So these are the last two questions on the test, number 11 and number 12. Up here we got use your following data to find the mass of a piece of metal. So we're going to find the mass of the water in the cup first. And to do that you would need to subtract. So it'd be 135.07 minus 2.24. The reason for that is because this is a cup in water with the water in it. This is the empty cup. So the difference between the two numbers would have to be the mass of the water. So 135.07 minus 2.24 is 132.83. Okay, down here you've got the same kind of a problem where you're doing the change in temperature of the water and you're just going to subtract. So you have 27.5 minus 22.07. So that would be a 3, that would be a 4, that would be a 5, and that would be a 0, so it's 5.43 degrees. The temperature of the boiling water was 100.4. So if you remember this lab, we had a beaker sitting here, we had a nut sitting in the beaker right here. And that was the water in that beaker was boiling, and the temperature of that water was 100.4. We took the nut from the beaker, put it into a styrofoam cup that had water in it, so that nut went from here to here. So the water in the styrofoam cup warmed, and the metal cooled. The change in temperature then would be the difference in temperature of this water and this water. So your beginning temperature was 100.4 for the metal. The final temperature of the metal would have been the same as the final temperature of the water, so it'd be 27.5. And that number came from right here. So our change in temperature would be 72.9 degrees C. All right, now for the heart of the lab, the idea is that Q of the metal, that is the quantity of heat that the metal lost, is equal to Q of the water. And the water gained heat. We know that this involves a temperature change. Both of these things change their temperature, but neither one of them changed from their current state of matter. The metal stayed solid, the water stayed liquid. So we're looking at one-step problems involving a change in temperature. So MCP delta T on one side. On the other side is MCP delta T. Okay, for the water, this side's the water side. We know that the mass of the water was 132.83 grams because we calculated that earlier. We know that the specific heat capacity of water is given to us right here. These are the specific heat capacities for both the metal and the water. So the water was 4.18. That's joules per gram degree C. And the change in temperature of the water was, from up above, 5.43 degrees. So we need to multiply those three numbers together. And I'm going to go ahead and do that. Move this down a little bit. So those three numbers together, multiply together, 132.83 times 5.43 times 4.18 equal 3014.90. That's rounded. 3014.90. On the other side, we don't know the mass of the metal. That's what we're trying to find. We do know, I'm gonna put it up here. We do know that the specific heat capacity is 0.449. That again came from up above. And we know that the change in temperature of the metal was 72.9 degrees. Once again, that came from up above. That number is joules per gram degree C. All right, now I need to multiply the 0.449 times 72.9, so 0.449 times 72.9, and I get 32.7. So M times 32.7 equals 3014.9. The units here, that one is joules because grams canceled and C's canceled. There's a C up here. So all you're left with is joules. Over here, degrees C cancel. Oops, don't want to do that. The degrees C cancel. And the unit would be joules over grams. Then when you divide these, you're going to simplify and get M by itself. When you do that, joules cancel and you're left with grams. So we needed to isolate the M. Some confusion has, I've seen lots of students unsure about what to do here. You divide both sides by the number that is with the variable. So in this case, that's 32.7. So on the left side, the 32.7s, they cancel. Oops. So everything over here is gone. Then we have to divide 3014.90 and 32.7. So 3014.90 divided by 32.7 is 92.2. So the mass of this metal, according to our data, is 92.2 grams. Once again, the idea is that heat lost and heat gained should be the same. Now we're on this actually is number 12, mislabeled on this test. So we had a fire. Here's a fire. It's in a Bunsen burner. In the fire, we had a bolt. And we were assuming that the temperature of the bolt would be the same as the temperature of the flame since the bolt was hanging in the flame. So to do that, the big picture is that we're going to take this hot bolt and put it in cold water, and the heat lost by the bolt would equal the heat gained by the water. If we knew the heat lost by the bolt, then we could find the change in temperature of the bolt. And from that, we could find the initial temperature of the bolt because we would also know the final temperature of the bolt. It's right here. This is the final temperature of the bolt. Okay, so the first thing you need to do is find the mass of the water. So that'd be 143.80 minus 1.80. So the mass of the water is 142. It's 142 grams. All right. So 142. The change in temperature of the water, we've got the initial and the final temperature, so we'd have 53.5 and 23.1. So we subtract, you get 4, you get 0, you get 3, so you get 30.4. And that would be the change in temperature, that's degrees C. Q of the water, you know that Q is equal to mCp delta T. And we know that it's only this formula because we had a 30-degree change from 23 to 53, so that's certainly within the liquid range of water. Plus, you did the lab and you know that it didn't change phases. So the mass of the water was 142. The specific heat capacity of the water is 4.18 joules per gram degree C. It's an 8. And the change in temperature of the water was 30.4. All right, so C's cancel, grams cancel, and we're going to end up with joules in our answer. So 142 times 4.18 times 30.4, we get 18,044, just rounding off to the nearest whole number, 18,044, and that would be joules. And really, if we were being strict with our significant figures, we would say it's really just 180, 1.8 times 10 to the fifth, but we're not going to use the significant figure rules. So 1.80 times 10 to the fifth, what it should be, we'll just call it, or excuse me, 10 to the fourth. 1.80 times 10 to the fourth is what we would call it, but if we were really being picky, but we're not going to worry about that. So we'll just round off to the nearest whole number. All right, now we're going to assume that Q of the water is the same as Q of the metal because we put that hot bolt into the cold water. So if that's the case, for the metal, the Q of the metal equals the mass of the metal, specific heat capacity of the metal, the change in temperature of the metal. Q of the metal we just calculated because it's the same as Q of the water. The mass of the metal we know because it says at the top of the page it's 55.76. So 55.76 grams. Specific heat capacity of the metal we know is 0.449 from the data at the top of the page. That's joules per gram degree C. And we don't know the delta T, so we're going to solve for that. So we know that 18,044 equals the product of these two numbers times delta T. So let's go ahead and work that out. So 55.76 multiplied by 0.449 is 25.04. So I'd have 25.04 delta T, and that equals 18,044. Now, how do you solve for delta T? Well, you need to divide by 25.04 on both sides, because this is multiplied by delta T, so the opposite of multiplication is division. All right, in terms of units, everything over here is going to cancel. So I would have grams canceling. There, degrees centigrade would cancel. Nope, I take it back. Degrees centigrade won't cancel because there's nothing up here to cancel it. Okay, so on this unit, I'd have joules per degree C. Having a little trouble with my pen here, as usual. Okay, so I'd have joules per C, so that's all going to cancel out. On this side, I'm going to have joules divided by joules per degree C. It was divided by. When I do that, I'm going to invert and multiply, end up with just degrees C. So 180.44 divided by 18044, not 180.44, 18,044 divided by 25.04. So 18,044 divided by 25.04 is 720.6. So delta T running out of room there. So delta T equals 720.6 C. All right, if you are going to then find Ti, we know that the bolt was hanging up here at the top. I had this picture drawn. It's hanging in that flame. When I put it into the cup, I'm going to get some change in temperature, and it's going to equal whatever the flame temperature was right here, minus whatever the final temperature of the water was. So if I wanted to find Ti, I would need to do the opposite operation. So it's minus Tf, so I'm going to add Tf to both sides. So plus Tf, plus Tf. So it turns out that Ti is equal to delta T plus T final. So now if we go down to the bottom and show that, we know that delta T equals T I minus Tf, or delta T plus Tf equals Ti. So if I add 720, I'm going to take this up here to an open space right here. So if I take my 720.6, add to that 53.5, do you know where the 53.5 came from? It's right there. That's the final temperature of the water. Add those two numbers together, so 720.6 plus 53.5, 774.1. And that is the flame temperature. And that's the end of that problem.